Pulse Width Modulation, or PWM, is a highly effective and versatile technique widely used in variable frequency drives, VFDs, to regulate motor speed and torque with precision. This method operates by rapidly switching the IGBT devices on and off at high frequencies, creating a sequence of pulses with varying widths. These pulses' width are adjusted in such a manner that the power delivered to the motor is controlled. The higher the width, higher the power fed into. The fundamental principle of PWM is that the width of every pulse determines the average voltage that is supplied to the motor, which subsequently determines its speed and torque output. Modulating the pulse duration carefully gives an exceptional level of control over motor performance. For this reason, PWM is considered a quintessential tool in modern motor control systems. Let's now discuss the interesting interrelation between PWM and sine waves. A sine wave is the closest to smooth, continuous, and symmetric. Thus, an ideal waveform for efficient power transmission it is. However, when applying pulses generated PWM to the winding of motor, the resulting wave is generated by inductance effect of winding. We can approximate get a sine wave by carefully adjusting the width of each pulse so that over time, the waveform closely approximates a smooth sine wave. This technique, known as pulse width modulation synthesis, allows us to successfully simulate a sine wave by varying the duty cycle of the pulses in synchronization with the desired output frequency. As the width of every pulse increases, so does the average voltage fed to the motor, and hence the power output increases and the rotational speed increases. In contrast, a thinning of the pulse width causes the average voltage to decrease, thereby reducing the power and decelerating the motor. Voltage regulation at this precision makes the motor function at its optimal efficiency over a broad range of speed without losing too much power in the system or producing excessive heat. With such approach, engineers would be able to develop control motors with slight acceleration, deceleration, and constant running conditions just like the sine natural wave. The actual power of PWM is in providing the best motor control while taking care that the system is energy efficient. Traditional methods of controlling the speed of motors often involve resistive component or transformers that dissipate a huge amount of energy in the form of heat. In contrast, PWM-based systems reduce energy loss since the power switches are either on or off. This significantly reduces inefficiencies due to partial conduction. That is why PWM is preferred for modern motor drives, as it strikes a balance between precision control, energy savings, and reliable performance. In conclusion, pulse width modulation is a very advanced technique in the way it revolutionizes control of motor speed and torque. It can be used to effectively simulate the sine wave behavior by rapidly switching power states and modulating pulse widths, thereby ensuring smooth and efficient motor operation. It finds applications not only in motor control, but also in power inverters, audio signal processing, LED dimming, and many other applications where precise power regulation is needed. As technology advances, PWM continues to play a vital role in the optimization of the performance of electrical and electronic systems, demonstrating the indispensable value it holds in modern engineering.